Hello everyone and welcome to this lecture on Poisson models. So binomial models can be used to model a count of events. Oftentimes we refer to these events as successes. In a given maximum count, and generally we call that maximum count the number of trials. So the number of trials is essentially the maximum possible count that we could have. So for example, we can model with binomial models the probability that a person is categorized as clinical versus non-clinical by using as an outcome variable the count or the rate of individuals characterized as clinical. However, to use this model, we need a number of trials. So in our example, that would be the number of individuals that have been tested. So what happens when we study counts for which there actually is no maximum, or maybe we more realistically think there is a maximum, but we don't know what it is exactly. We just know that it's possibly a very large number. So Poisson models are widely used to model outcomes that are counts of events or rates of events that do not have a defined upper bound. So this means here that we're going to predict counts or rates that could virtually take any positive integer value. So for example, we could think of the count of clicks on a website in a given day, given that there is no restriction on how many times the website can be visited. That could be the count of apples sold in a month by a grocery store, given that the store doesn't run out of apples to sell. Or another example, that could be the number of people that go to see a movie, given that there is no restriction to how many people could go to see the movie. So the idea here is that we have an infinite number of trials, or at least we'll assume that. In general, it is not really infinite. For example, the count of apples sold in a month is not really infinite, because in fact the store could run out of apples to sell. And there's also a finite number of apples that could be sold in general, or that exist. The count of clicks on a website may be limited by some technological factor. Maybe the server would crash past a certain number of clicks. However, it does not really matter so much. What we really assume, and really all we need here, is that this number of trials may not be really infinite, but what matters is that it's unknown and much larger than the number of events observed. So in a sense, we could think of it, of this situation as the number, let's say the number of apples sold, is always going to be a really small part of the apples that could be sold. So in a sense, the number of trials is considered infinitely larger than the actual counts, than the observations. So let's talk about the example data that we're going to use. We'll use the Anscombe dataset, which is part of the card data package for R. It contains per capita education expenditures in dollars for the 50 states of the US plus Washington, D.C. And so we will study the states' education expenditures, which is in a variable education. So this will be our outcome variable. And we're going to try to study it, try to predict it using various independent variables. I'm going to use the income per capita, and we're going to use the proportion of residents per thousand that are below 18 years old. Alternatively, we'll also study the effect of this variable, but using a discretized version of it, splitting the variables in two groups with a cutoff of 400. So we're going to use this Young variable in a numeric format, but also in a dichotomous format. So we hypothesize that the larger the income per capita and the larger the proportion of residents below 18 years old, the larger the education expenditures per capita. And we also want to study the possible interaction between these variables. So this is what the data looks like. And so that's what we are going to study here. So first off, let's start by looking at a histogram of the outcome and see what we can say about it. So, it seems like we see most observations somewhere between 150 to 250, and we see that obviously we have a floor at 0, cannot have spent less than 0, so there is actually a floor here, and that doesn't really seem to be a ceiling, because it seems like we have a few outliers, perhaps around between 350 and 400. So it's interesting that we have that shape, that skewness in this distribution, and that's something we're going to talk about later on. So further exploring the data, let's look at the relation between income and education. So it seems like we have a relation between the two. It seems like as income is larger, education tends to increase. However, it looks fairly linear, but we see that there are a few points that are maybe outside of that, and it also seems like there's more noise as you increase income. So as you look at the right of this graph, we tend to see more spread in the observations than if you go and look at the left of this chart and predict lower education expenditures. That's also something we're going to talk about. We're going to talk about dispersion. Now, if we also combine with the age variable, which in this case is that discretized or dichotomized version, with a cutoff of I don't remember the number, I think it was 400. So we see that it seems like we have somewhat the same type of relation between income and education, even when there are a lot of people characterized as young in this data set. Okay. So before we actually go and do a Poisson regression on that type of outcome, we need to talk a little bit about the Poisson distribution, which will allow us to see why it is a good distribution for that type of data. So the Poisson distribution is a discrete probability distribution, which is particularly fitting when we have counts, because counts are also discrete. They take values 0, 1, 2, 3, 4, 5, etc. So it is fitting that we use a distribution that is discrete, that is a discrete probability distribution. And so it gives the probability of a count of events occurring in a given interval of time and space. So it is particularly interesting, of course, in this situation. So the Poisson distribution assumes that the events arrive independently, which is something we're going to assume here, which may not be completely correct, in fact, in this data set, but we're going to still assume it. So the events arrive independently. This means that in this case, right, if we think of our outcome variable, expenditure in education, what this means is that we're assuming that every dollar spent is independent from the next, or any other. That's an important assumption, which probably is reasonable given this, the scale of the variable that we're studying. But of course, it's not exactly true. For example, let's say that the state decides to purchase, let's say, a new computers for a classroom. They have to spend a batch of money, right? They cannot spend just, let's say, $1, right? So obviously, this is not exactly true that the spending of each dollar is independent in this case from the spending of another dollar, or the non-spending of it is also not really independent from the non-spending of another dollar. However, we're going to assume that it's relatively correct. Again, given the scale, it probably somewhat is. At least that's important to note this assumption. And so another assumption that we're going to make is that the rate of spending is constant. So in our data set, again, what that means is that the expenditure of $1 does not imply the expenditure of another dollar, and the state spend at each state spends at a constant rate. So this rate is in fact the only parameter in a Poisson distribution to characterize a Poisson distribution. This rate, we generally refer to it as lambda. And so it is named the rate parameter, logically. And so again, it's the only parameter of a Poisson distribution. So just knowing lambda tells us, defines completely a Poisson distribution. So it's not like, let's say, the Gaussian distribution, which has a mean and standard deviation or variance. In this case, we have only one parameter. Another example of a distribution that only has one parameter could be the Bernoulli distribution, which has only one parameter, which is the probability of the event to occur. So the Poisson distribution only has one parameter, and so it can be written this way. We don't need necessarily to remember this formula, but this is the formula here that gives us the probability mass for each count. So let's say that we want to predict a given count, and we're going to call this count K. We apply this formula to get the probability of observing a count equal to K. And so, by the way, K with an exclamation point is what we call the factorial of K. So it's let's say that K is 4. It's 1 times 2 times 3 times 4. So we could apply this formula, but in general, it is already included in many software, so that we don't have to actually compute it from scratch. And so we don't have to rememorize this formula for what we're going to do next. Just wanted to show what it looks like, but we don't have to memorize it afterwards. Okay, so this is what the Poisson distribution looks like, for example, for a rate of 0.2. So here we have set lambda, the rate, to 0.2. And so that's enough to define our Poisson distribution. And so if we compute the probabilities for each count, the probability masses for each count, we can compute it, of course, for every number, every integer number starting from 0, because it's a count. So we can compute it for 0, for 1, for 2, etc., which is what we did here. I stopped at 20, but there is actually, it could go up to infinity, basically. There's no upper limit. There's no ceiling. There's only a floor at 0. And so we see, for example, that here the probability to observe a count of 0 is about 0.8, a little more than that. And the probability to observe a count of 1 is about, let's see, looks like it's about 0.18. And then the probability to observe a count of 3 further decreases. It looks like maybe it's 0.02 or something like that. And we see that we still have a tiny bit of probability afterwards, and then it's so small that we cannot see it. And this is going to make sense later on, but a little preview here is that the rate actually is also the expectation. So it's also the expected count. So it makes sense that if we expect, if our expectation for a count is 0.2, that in most cases we're going to observe 0 or 1, which will give us, in few occasions, maybe 3, and in even fewer occasions 4, etc. So of course this makes sense if we consider that the rate is 0.2, so it's a very low rate. And if we consider that this is also the expectation for the counts. So what if we increased a little bit this lambda parameter? So now we have a lambda parameter of 1. And so this is what the Poisson distribution looks like. So again, lambda is the rate, but it's also the expected count. And so we see that if we expect a count of 1, we're actually going to have, most probably, counts of 0 with probability of, let's see, it looks like it's 0.36 or something like that. For 1, probability to observe a 1, we actually see that this probability is about similar, so around 0.33. To observe a 3, a count of 3, we see that the probability starts to decrease at around let's say 18 or something like that, and then it further decreases. So again, I've increased from the rate from 0.2 to 1. So then I'm not going to comment all of these probabilities that we see, but what we're going to see is that as we increase the rate, naturally, right, because the expectation is larger, because the rate is larger, then we're going to have larger probabilities for counts that are larger than 0, right, that are more and more positive, obviously. And so we're going to still see that skewed distribution, however. Right, so 0.2, a rate of 0.2, rate of 1, rate of 2, rate of 3, rate of 5, a rate of 7, and probably you see already something going on here, which is that as I increase the rate, the distribution looks more and more like a normal distribution. And that's something we're going to talk about also. So let's talk a little bit about we've talked about this expected count already. So we've already said that as a preview. The expectation for the count is equal to the rate parameter lambda, which is somewhat self-explanatory. That's a little bit the definition of a rate anyway. However, what is interesting here also is that in this distribution, again, there is no variance parameter, but there actually is a variance because, of course, we have different counts that can be made. And actually, what's interesting is that not only the expectation for the count, but also the variance of these counts is going to be equal to the lambda parameter. So it's an interesting feature here, that is that the rate is also equal to the variance. And another interesting feature is that the expectation is equal to the variance. And notably, this is different from what we have known from Gaussian models, where the variance is in fact fixed. The variance in Gaussian models is different from the mean, notably. So it's different from the expectation. It doesn't have to be, but what's interesting is that it's not related to it. It is actually fixed. That's the assumption of homoscedasticity, also called homogeneity of variance. So in Poisson model, we actually have an assumption on the variance, but this assumption is different. It's an assumption of equidispersion. That's the name that we give to this assumption. And as the term equidispersion indicates, we are assuming here, because that's what the Poisson distribution, that's how the Poisson distribution is defined. We're assuming here that the expectation is equal to the variance. So what that concretely means is that if I'm going to predict a high rate, I'm also going to make more errors. So I'm going to have a high variance. If I'm predicting a low rate, I'm going to have lower variance. Okay. And by the way, if I go back to what I've seen here, this is a little bit what I see, right? As I increase the predicted rate. So if you look on you can look either on the X scale or Y scale, but in this case, that would be the Y scale, that would be the outcome. You see that if I predict high education expenditure, so a high rate, it seems like I would be making more errors, there's more spread than if I predict a low expenditure in education, right? So a low rate. So this also seems to work very well, but still, I'm going to talk about that towards the end. But there are some cases in which, for which this assumption can be not realistic. We're going to talk about what to do about that. Okay. So something we also have seen graphically, there are mathematical proofs of that, is that as I increase the rate, the Poisson distribution will tend actually to a normal distribution. This tendency for the Poisson distribution to be more and more normal as the rate increases means that if you predict large rates, it's not necessarily going to make much sense to use a Poisson model, which is sometimes slower to fit, maybe less interpretable, etc. So in other words, corollary of that is that the Poisson distribution is going to have an added value that is especially important when we have counts of events that are somewhat rare, right? So with a low rate. So the Poisson distribution can be seen also as a limit case of the binomial distribution. And so if we think of the binomial distribution, again, it gives us the count of events, an expected count of events. Count of events, given the probability of the event to occur and given the number of trials, P for the probability and N for the trials. So what's interesting here is that if we take this binomial distribution and we increase N times P, so the probability of the event to occur times N, so times the number of trials, which actually can be thought of as a rate, right? Because N times P is the expected count in a binomial distribution. So it couldn't be seen as a rate, we could be calling it a rate. So if we multiply P times N and we just fix that value, so we fix N times P, but we increase the number of trials. So for the same rate, but increasing the number of trials. So in other words, as we increase N, number of trials, we would need to decrease proportionally the probability in order to maintain N times P constant. So again, if I fix N times P, number of trials times probability of success, but I increase the number of trials, I'm going to have a distribution, binomial distribution, that is going to tend to the Poisson distribution. So this is known as the law of rare events, also known as the Poisson limit theorem. So we're going to see an illustration of that graphically. So let's say here, for this example, I'm going to say that I have a binomial distribution with N is equal to 1. So I only have one trial, and the probability is 0.5. So this is actually like a Bernoulli distribution with probability 0.5. So you can think of it as tossing a coin, and let's say you get a score of 1 for heads, a score of 0 for tails. So this is what the distribution looks like. This is what the probabilities look like. You actually have half a probability of 0.5 of the event not occurring at all, so 0 times, and a probability of 0.5 that it occurs 1 time. And nothing else, which makes sense because in a binomial distribution with only one trial, the event can only occur once or not at all. Right? So these are the only two possibilities. What is the rate in this example? The rate is the predicted count, the expected count. So it's calculated as N times P. So 1 times 0.5. So the rate is 0.5. So what we can do is now say, okay, a rate of 0.5, an expected count of 0.5, let's see what it looks like in a Poisson distribution. So this is what it looks like in a Poisson distribution. So this is a Poisson distribution with rate 0.5. So we have the same rate, but two different distributions to represent it. Now we see that what's interesting here is that the Poisson distribution doesn't have an upper bound. There's an theoretically infinite number of trials, as opposed to the binomial has only one trial here in this example. Okay, so we're going to fix this rate to 0.5, and I'm going to change the binomial distribution. So rather than one trial and a probability of 0.5, I'm going to keep constant the product of the two, the rate, 0.5. But this time, I'm going to have a situation where n is 2 and p is 0.25. Now we see that the expected count hasn't changed. N times p is 2 times 0.25. So the rate actually is still 0.5. So the expected count is still 0.5. However, here we have two trials. So here we have a different distribution for the binomial distribution. So we see that we have decreasing probabilities here, with 0 seems to have a probability of, let's say, 0.55, 1 maybe 0.38 or something like that, and 2 seems to be around 0.05, and nothing else. Why nothing else? Well, because there are only two trials. So the event can only occur twice, that's the maximum. Can it occur 0 times, 1 time, or 2 times? Okay, let's look now at, again, the same Poisson distribution. This hasn't changed, it's going to be exactly the same here. So same as the Poisson distribution we had earlier. It hasn't changed because it has only one parameter, that's the rate, and we haven't changed it. Okay. But what you see happening here is that as I take my binomial distribution with the same rate, so I keep the same rate, but I increase n right here, it seems like I have a distribution that looks more like a Poisson distribution. And in fact, if I do that more dramatically, so let's say here that I have a binomial distribution with n equal to 100 and p equal to 0.005, that is still the same rate. Right? That's still the same rate of 0.5 because it's calculated the rate as n times p. So it's still a rate of 0.5 that I have here. But what you see when you look at the distribution is you see a distribution that in fact is very, 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 very close to the Poisson distribution. Cannot even distinguish them, or really only slightly. And if I do that even more, we'll see that, so here binomial with n is 1000 and p is equal to 0.0005, so still the same rate of 0.5, calculated again as n times p. Then you see that I really see no difference between my binomial distribution and my Poisson distribution. And so that's an illustration for the Poisson limit theorem, or law of rare events. So if I take a binomial distribution and I keep the rate n times p constant, but I increase the number of trials, my distribution is going to tend to a Poisson distribution of that rate. Okay, so now let's connect the Poisson distribution to a tool that we have talked about previously, which is generalized linear modeling. As a reminder, generalized linear modeling is a modeling framework that has three main components, which are the linear predictor, which is sometimes referred to as eta. So it's the beta 0 plus beta 1x1 plus beta 2x2 plus beta 3x3, so on and so forth, with possibly some interactions, some categorical predictors included as dummy variables, etc. So that's the linear predictor. It's a component that we also find in linear modeling, general linear modeling. But a new part here in generalized linear modeling as opposed to linear modeling is that we also have a link function which links the expectation of the outcome to the linear predictor. So this time the expectation of the outcome is not equal to the linear predictor, but it's equal to some function of it. And another way to say that is that a function of the expectation is equal to the linear predictor. So depending on whether we put the function on one side of the equation or the other side, we have either the link function or the inverse link function. That's what the G seemingly subscript -1 means. It means the inverse of G, the inverse function. So, and there's a last component, which is of course very important, is that we also can use a probability distribution function from the exponential family, which includes the normal distribution, but also includes other distribution, including the Poisson distribution. Poisson distribution is part of the exponential family of distribution, meaning we can use it in generalized linear modeling, and we will. And so we're going to talk about the link function now. So the link function is in fact going to be the logarithm, and so that's the reason for calling the models we're going to use log linear. So the log linear Poisson model, commonly referred to as Poisson regression, that's probably the most common name for Poisson models, for log linear Poisson models, is to just call them Poisson regression. So it uses the Poisson distribution as a distribution model for the outcome, and it predicts the rate parameter of that distribution. Obviously, that's the only parameter really to predict here. And it uses as a link function G the natural logarithm function. Sometimes this is written as ln, sometimes this is written as log, because oftentimes when you type in most calculators log, the calculators or software log, the default is to use the natural logarithm. And sometimes it is written log with base e, and base e is written as a subscript to log, typically in most common notations. And so, ln for natural logarithm, log, because usually that's the default, or log with subscript e, so log in base e it's called, is here the link function G. So the inverse of this link function, the inverse of the natural logarithm function, is in fact the exponential function. So it's e to the power of. So these are really the main things to know here, the most central things to know. The linear predictor doesn't change, but the link function is the logarithm, meaning that the inverse link function is the inverse of that, which is the exponential function. And the distribution we use for the outcome variable is the Poisson distribution. And so the rate is given, if we condense these equations, the rate is the exponential of the linear predictor. So we talked about this. So log linears use as link function the natural logarithm function, ln, or log e, or simply log. And so for this reason, that's why we call these most Poisson models log linear models. An important note, most times when Poisson models are used, the logarithm is used as a link. However, this is not a requirement of Poisson models, and other links can be used. For example, the identity link can also be used with a Poisson model. Nevertheless, when Poisson regression or Poisson models is mentioned, it is generally implied, and you should in general imply, unless stated otherwise, that a logarithm link has been used. The inverse link function, as we said, is the exponential function. Okay. So in our first model, we will investigate the effect of income only as the main and really only predictor, and then we're going to add our other predictor later on. So we will write our model this way. The logarithm of lambda is what we predict. The logarithm of lambda is equal to beta 0 plus beta 1 income. So really, that's really all there is to understand here, is that, well, rather than predict directly the rate, we will actually predict a function of the rate, and that function is the link function. So it is the logarithm function. And of course, we define the distribution for education as a Poisson distribution. That's our model. So now, how do we estimate this model? In other words, how do we find parameter values here? The estimation of parameters is generally done through maximum likelihood, ML, estimation, which, contrary to linear models, cannot be simplified by ordinary least squares, and is thus generally done iteratively using various optimization algorithms. Most software packages are capable of estimating models like this. Should have written log linear models, because that's what I meant here. So most software can actually do that. Poisson models with log links are really a classic, at least of generalized linear models. So it's very frequent that they are included, at least whenever generalized linear models are possible. So when we are working with SPSS, for example, within the generalized linear models menu, we see that we can actually directly select Poisson log linear, which will use the log as link and the Poisson distribution as a distribution. And then we provide our dependent variable. Then we provide our predictors. So in this case, we only use income. We also have a menu to define our model, so that's useful if we want to include some interactions. And then we can choose what type of test we want and what type of output we want. And notably, what we want to do in general, if it's not too costly computationally to do that, is to use likelihood ratio tests. And also, we usually parameter estimates are usually better interpreted using exponentiated versions. We're going to talk about that later on. So it's important to check a box and make sure that in the menus we're going to have these exponentiated estimates. Otherwise, it's not so bad. We can also exponentiate them ourselves. But it's more convenient if we can do that directly within the software. And so as an output, one of the outputs that we get is these parameter estimates. So we get here an estimate for the intercept and for the slope. For the effect of income, so these are the estimates for the parameters is B, their standard error. We also have their confidence intervals. We have world chi-square test. In this example, you can choose otherwise. World chi-square tests for the intercept and for the slope with their p-values. And I've also checked here the exponentiated estimates along with confidence intervals for them. Interesting note is that some software, notably SPSS, output world chi-square test with degrees of freedom 1 instead of world z tests. So the p-value should be the same, and in this specific situation you can easily convert z to chi-square through just squaring z or taking the square root of the chi-square value. So it doesn't really matter, you should get the same p-value anyway, but that may explain some inconsistencies that may appear between software, that some software compute world chi-square tests as opposed to world z tests. It doesn't change the interpretation, nor it shouldn't also change the p-value. Okay, so let's talk now about model fit. So model fit is generally tested through a nested model comparison using a likelihood ratio test, generally in the form of a chi-square test, where the candidate model is used as the full model. So in this example, that's beta 0 plus beta 1 times income. And the null model is an intercept-only model that only includes beta 0. So fx can be tested using using a nested model comparison strategy, which are sometimes referred to as analysis of deviance as opposed to analysis of variance, but it's the same idea of strategies. You have type 1, type 2, and type 3. As a reminder, type 1 is sequential. It starts from the first predictor to the last. Type 2 and type 3 consist in comparing a complete model with all predictors, with a model with all predictors except the one of interest. And the nuance between type 2 and type 3 is that type 2 may change models in order to respect the marginality principle. In other words, when you have an interaction and you're testing main effects, it removes the interaction in order to test the main effects. That's a simplified version of it, but that's the idea. Versus type 3, which doesn't do anything. It just keeps the complete model regardless of whether there are interactions or not. Okay. So the null hypothesis of the likelihood ratio test can be stated as: the model does not predict the outcome any better than the null model in the population. You can, for example, express this mathematically with maximized likelihoods. So if we think of the likelihood as it has been maximized, so in other words, the model has been fit. So the null hypothesis can be stated as: the likelihood of the full model is equal to the likelihood of the null model in the population. And so the alternate hypothesis is that the likelihood has improved from using the full model as opposed to the null model. So the likelihood of the full model is larger than the likelihood of the null model. Now we know that these are actually transformed, these likelihoods, in order to make the test, because that's more practical. They're notably transformed in -2 times log likelihoods. So in a metric that we call the deviance, which is -2 times the log likelihood. And what's interesting about doing this computation of -2 log likelihood is that, well, first off, it simplifies a lot of calculations to do that, to think in terms of deviances rather than likelihoods. But also, what it allows us to do is chi-square tests, because deviance statistics are chi-square distributed. So that allows us, in other words, to get p-values. So in SPSS, for example, we get a likelihood ratio chi-square test. And chi-square is in fact the difference between the is in fact computed as the difference between deviances of residual deviances of the null and full model. And so here in this example, we see that we have notably a significant effect of income, the p-value below 0.001. So as a measure of observed model fit, we can use various statistics, but usually we use a pseudo R-square. However, they are not computed in SPSS, even though they can be computed manually. An interesting note to make, perhaps, is that pseudo R-squares are most commonly reported for logistic regression and not so much for other types of generalized linear models, even though they can be computed using similar formula. But they are less heavily studied and so less reported, and also the fact that probably they're not included in SPSS, at least currently, is probably a reason for them being less reported. So it's less frequent to report pseudo R-squares in the case of Poisson regression than in the case of logistic regression. So we could conclude here, could write this up, for example, by saying a likelihood ratio test showed or indicated that the model significantly predicted, should have written, education expenditure. And so we can provide the R-square, chi-square with degrees of freedom 243, degrees of freedom 1, and chi-square value is 243.6, which we find here. And the p-value is below 0.001. You could also write, because there's only one predictor here, you could say income had a significant effect on the education expenditure. and again with the same statistics. In general, what's important to note, and this is true of all generalized linear models that are not the particular case, which is linear models, it's important to note that Wald tests are only asymptotically equivalent to likelihood ratio tests. And they actually both, likelihood ratio tests take the shape most frequently of chi-square tests. Wald tests perhaps a little less frequently, but in SPSS they do. So what that means is that if you use a chi-square test, it is generally preferable to be clear about what test you used, whether you used a likelihood ratio test or a Wald test. And it is usually preferable to use a likelihood ratio test. Okay, so how do we interpret now a Poisson regression model? So again, going back to the estimates here, generally when we interpret linear models or generalized linear models, we look at estimates, and especially here, we are particularly interested in the effect of income, so we are probably going to be interested in the slope estimate. But there are cases in which we might be interested in the intercept, so we're still going to interpret this. So the intercept is the predicted logarithm of education expenditure for an income equal to 0. So in other words, here, this 4.365 is the predicted logarithm of education expenditure if the state that we're studying had an income of 0. It's not exactly the state that has an income of 0, but as a shortcut, I'm just going to say the state has an income, a value for the income variable that is equal to 0. Okay, it's not very interpretable because probably no state has that. Usually, of course, we don't interpret the intercept. There are only a few exceptions. Usually, and here, we're interested in the effect of income instead. So let's talk about the slope. So the slope here is the predicted change in the logarithm of expenditure for each dollar increase in income. So if we come back here, so unfortunately it is very low in this data set. It seems very low, but actually is a significant effect. It's just that the way the variables are scaled give us very values that seem very, very low, but in fact it's a significant effect. So what that means is that this slope that we see is the predicted change in the logarithm of expenditure for each dollar increase in income. And again, it's the logarithm because we have this link function that we put here in order for us to do this analysis. So the logarithm is not very convenient. We're not used to talk in terms of logarithms. So it's much easier to remove the logarithm. So the way we remove logarithm is usually by exponentiating any logarithm of something. And so that's what we're going to do here, and that's why we asked for the exponentiated versions of these estimates. So what if we used exponentials here? So the exponential of the intercept, which by the way, let's not make this too complicated. The exponential of the intercept, we see it here, it's on the nearly on the right here, it's exponent of b, right? And so it's 78.627 in fact in this example. So the exponential of the intercept is the predicted education expenditure for an income equal to 0. So this time I have directly a predicted education expenditure, provided just that instead of interpreting the intercept, I interpret the exponential of the intercept. So e to the power of the intercept. And for the slope, the exponential of the slope is the predicted multiplicative change in the education expenditure for each $1 increase in income. So what that means is that expenditure is multiplied by this exponential of the slope for each $1 increase in income. And so usually, because it's a multiplicative change that we have here with exponential of the slope, then of course we will compare this exponentiated coefficient, right, exponent of the slope, we will compare it with 1. Because if it is above 1, then the rate, and therefore the expected expenditure, increases as the predictor increases. Right? So it's multiplied each time by a value above 1, so it increases. But if it is below 1, then the rate, and therefore the expected expenditure, will decrease as the predictor increases. So in this case, unfortunately, we cannot really see much here because of the way the variables are scaled, but the exponent of b actually rounds to 1, it seems. That's because of how the variables are scaled here. But we see that we still have a significant effect. So how can we better study in this example? So usually that doesn't happen because this depends really on how the variables are scaled. So maybe if we had expressed income in terms of thousands of dollars or something like that, it would have been different. So if we had changed the scale of the variables, it might be slightly more interpretable than here. Okay, so how do we make predictions based on this model here? So predictions are made by applying the model formula. And if we want predictions in the scale of the response variable, y, so in this case, education expenditure, then we have to use the inverse link, which is the exponential. So we will here take the exponential of beta 0 plus beta 1 x1, and of course, now that we have estimates, we will use the estimates, which is why we have a little hat over beta 0 and beta 1, is that now we actually have values. So in order to make a prediction, we are just going to plug in values here. So it is really very similar to what we have in linear models, with, of course, that inverse link here, which is the exponential that we see. But that's really all there is that's new here. Okay, now how do we make plots here? So for models with one predictor, a typical plot we would make is we would plot the expectation of the outcome, so the predicted rate, as a function of the predictor. So here that's income. And so we often want to plot the data on the same plot, like we usually do in linear regression, for example. So here the outcome is count observation, so both the expectation and the data are directly on the same scale. So we have really nothing to change whenever we need to make plots for this regarding the scale. It's slightly different than for logistic regression, where usually if we have a dichotomous variable, let's say it's yes, no, then we have to recode it to be numeric with zeros and ones. So if we have more than one predictor, we can use alternate ways of representing variables, such as grids or layers, and I'll talk about that later on. So let's say that this is our data again. So same thing, this is just the data. Now I will add my predictions for the rate as a function of income from my model, and I have this model here. So this is a Poisson model. This is the log linear model. And so we see that it's actually not exactly a straight line. We see that little exponential shape a little bit here on this plot, which seems to represent quite well the data. So now let's talk about how we make these models slightly more complex. How do we include additional terms in our models? So both numeric and categorical predictors can be added. in a manner similar to analysis of covariance in linear models. So what that means is that if you know how to perform an ANCOVA or a one-way ANOVA or even a factorial ANOVA, all of these, there's really nothing different here for Poisson models. The only things that are different are the link function and the fact that we use the Poisson distribution instead as our model. But the rest really remains the same. So categorical predictors, for example, are included through the use of dummy variables, like we do in ANOVA or ANCOVA. Interactions may be included between predictors, also, in a manner similar to the way they are included in linear models. So in other words, all of these other components that we may know, like moderation or interactions, same thing, or controlling for variables, using categorical predictors, using transform predictors like quadratic terms, let's say. All of that is still possible in a Poisson model. So, and is used really in the same way. So for example, here, if I wanted to add in my factor variable, which is a Young group, so here that's my dichotomized variable for the count of people under the age of 18, I think it was. I can add it here, and then I just add it to my model. That's without interaction. And if I wanted an interaction, I would add it here. That's really it. So a new thing also, if you're using SPSS, to note is that you can actually get predictions whenever you have a group predictor. You can get what are called estimated marginal means. That means that you can get predictions for each of the groups. And so if you have numeric predictors, that will hold these numeric predictors constant, fixed to their mean, in order for the software to compute these marginal means. So what does that look like in this example? I want to use, in fact, the example with an interaction here. So I have income, the group variable, and their interaction. Again, the group variable here is dichotomous, so it's going to be represented by one dummy variable. Now, even though it is represented by only one dummy variable, we actually see two dummy variables, even though one has is actually set to 0. That's part of the way the outcome is presented here. So we see that for Young group is equal to high. We actually just have 0 for the slope of what that dummy would be, and for the interaction of that with income, it's also by definition set to 0. So here we wouldn't interpret these. Now, unfortunately, because we have an interaction term here, it's not going to be very easy, and also because these are not linear models, it's not going to be easy to really directly interpret a model like this. Usually what you would want to do is compute either estimated marginal means if you're focusing on the Young group variable, or better yet, you could also try to plot either estimated marginal means, but here we could try to plot both variables at the same time, income and the group variable, using, for example, income on the x-axis and the group variable using different colors. But first, let's test the effects. SPSS tests effects by default using a type 3 analysis of deviance, which again compares a full model which is the complete model with all predictors. So the intercept, obviously, income, Young group, and Young group times income, which is the interaction. And it compares it with a null model that includes everything but the term that is being tested. So here we see, well, the intercept is usually not studied here, but we see a significant effect of income, it seems. Not a significant effect of Young group. However, we see a significant interaction between Young group and income. So we're going to try to discuss that. Again, we also have estimated marginal mean, so predictions per the model for each of the groups whenever we have group variables. So here we have predictions for we have the prediction for the for the average group, which is 189, and the prediction for the high group, which is 260. So it is larger, the prediction that we make, which is in line with our hypothesis. So here, if we look at the data again, we have here, that would be a good way to plot the data, to use the horizontal axis for the predictor, for the covariate income, and of course education, which is our outcome variable, on the vertical axis. And we use here, as a way to distinguish between groups, different colors. That's one of the ways to do that. And so this is just the data. Now if we plot our model, we see that our model seems to represent quite well the data. Probably one of the important merits, I would say, of this model is that we seem to account better for a few of the outliers, especially the one that's really at the top right here through this model. It seems like we understand data a little bit better, and it's sort of like now we know why this point is so high, perhaps. Here, what we notably see in this interaction plot is that the relation between income and education is an increasing relation, but we see that it increases at a faster pace for the high group than for the average group. And again, we could use different colors, but also we could use a faceted plot like this if we want to crowd maybe the graph a little less. That's another way of doing that. Okay, so really essentially everything you may know about including covariates, including categorical predictors, including both at the same time, including interactions between categorical predictors, including interactions between a categorical and a numeric predictor, and including interactions between numeric predictors. All of that is perfectly applicable within the context of Poisson models, exactly like they are in the context of linear models. So something we haven't talked about, we just talked really briefly about, is the concept of equidispersion. Because after all, the distribution part of this model is also part of the model, right? So we not only make an assumption on the type of relation, on how the rate can be predicted, but we also make an assumption on how the distribution works. So in other words, on how the outcome is distributed, conditionally upon the predictors, of course. So Poisson models assume that the variance, we could call it the conditional variance, because here it's the variance of the distribution of the outcome conditional upon the predictors, or conditional upon the predictions. A little bit, by the way, very similarly to the conditional distribution that we study in linear models. So the variance of this outcome is equal to its mean, or equal to the expectation, or equal to the rate. And so this is known as the assumption of equidispersion. So what if it isn't true? Let's note that we have different words for when that is not true, and there are really only two possibilities. When that is not true, when we don't have equidispersion, either the variance is larger than it should in a Poisson distribution, so in other words, it's larger than the expectation, larger than the mean, or larger than the rate, and we call that overdispersion because we have more dispersion than we should. And the opposite, of course, is called underdispersion. That's when the variance is smaller than the expectation. So in real data, it is more frequent to see overdispersion than underdispersion in practice. So most of what you may find if you try to see how to compensate for problems of non-equidispersion relate more to overdispersion. So it's important to note there's a greater focus on over dispersion as an issue rather than under dispersion. Both are issues, but one is more heavily studied, and also one of the reasons for that is that usually there are more problems from over dispersion than under dispersion. So a typical test for this is consists in building an auxiliary regression model, a little bit like what we do for linear models with the Breusch-Bacon test, where we study how the variance changes could vary as a function of the predictor. But here instead, we build a model of the variance, an auxiliary regression model, where the variance is predicted by the expectation. So far so good, right? That's what it's supposed to be, equidispersion. But it's not only the expectation directly, it's the expectation plus some constant, some value, some number times the expectation. And so that's helpful, because if we specify things this way, like in this formula here, then we see that if we have an alpha of 0, the alpha times the expectation of y part becomes 0, right? And so the variance is then equal to the expectation. So in other words, we would have equidispersion. But if alpha is larger than 0, then the variance is larger than the expectation, and so we have overdispersion. If alpha is lower than 0, then the variance is lower than the expectation, so we have underdispersion. So that's it's interesting. It's interesting to use this formula, because then we can that gives us essentially a test of overdispersion or underdispersion. If alpha is larger than 0, we have overdispersion. The variance is larger than the mean. If alpha is lower than 0, we have underdispersion. And by the way, 1 plus alpha is often called the dispersion parameter. So there's an alternative for testing this, is that we could also study. We can also use the same formula, but instead of using alpha times the expectation of y, sometimes we square the expectation of y. Okay, so let's now talk about an extension of Poisson models, which is frequently used, which is to model counts and rates in intervals that are variable. So by default, Poisson models will assume that we study rates or counts of events that occur in a fixed interval of space or time. So for example, the number of clicks to a website per day. But it is also possible to use Poisson models when we model a rate or count of events in variable intervals, as long as we know what these intervals are. So for example, we may predict the number of clicks in a month, but we know that months don't have the same number of days. So if we know the number of days for each month, then we could use that and still use a Poisson model. We would just need to provide that new information, which is the number of days per month. That will give us the interval. Another example, we could count the number of trees in forests that have different sizes. So same thing, that we could count the rate of trees, even though we might have forests that have different sizes. Again, that information, that interval, the size of the forest here, can be provided. We can also count the number of clinical patients in hospitals that are in cities of different populations. So if we have more people in a city, then we might expect more clinical patients. So what we could do is control for that by including that as the interval here. So the technical term for that interval that we specify here, and that we have to know in order for us to do this, to do any analysis that will account for it, that's called the exposure. We generally refer to it as that. So let's say that we have different months, right? And we use the number of days of the month as exposure. Then January has an exposure of 31, February has an exposure of of 28. Okay, so let's say for the sake of the argument that the first 25 states used measures of expenditures in months with 31 days, while the rest used the expenditures in months with 30 days. So maybe we measured expenditure at different, among these states, they were measured for different months, and the months do not have the same number of days. Some of them use months with 31 days, some of them with 30 days. So maybe we measured in December for some of them and November for other ones. So let's say that we are interested in the effect of income for the sake of simplicity. So we're just going to study the effect of income here. So the question is, how do we account for the fact that we have a variable exposure here? That the fact that we don't have the same number of days. Now, of course, that could play a role because if you have more days, you have more days that you're able to spend money. So that's something we need to account for here. So we could build a Poisson model for the daily expenditure. And so that's what we could do. That's one way of doing that. And actually, some software allow you to do it this way instead. And we're going to see another way that we could do that, the same model. And so the idea here is that rather than, it's really natural, it's probably natural to think about this way of solving the problem, is that, well, rather than predict the expenditure per month, if we know that the months don't have the same days, here, what we could do is just compute the daily expenditure. So the expenditure per day instead. So what we would do for that is that rather than predict the original rate, we would predict the rate divided by the exposure. So divided by 30 or 31 in this example. And so that's one way of solving the problem. Just use the same model, but rather than predict daily expenditure, monthly expenditure, we now predict daily expenditure, and that accounts for the fact that we may have had different exposures. It's important also to know that when you do when you try to fit that model, you should not only do that manipulation where you take lambda and where you take the counts and you divide by the exposure. Not only should you do that, you should also weight observations by the exposure term. And this is to tell the software or tell the estimation procedure that in months of, whenever you used month of 31 days in this example, you actually had more information than month with 30 days. So that's not a piece of the puzzle here that's important to note, is that the exposure, of course, has a role on what we predict, but it also has a role on how much information we have. Right? We have more information if we have more days than if we have less days. So we also need to count, to take that into account. Right? In a sense, maybe a more extreme example would be if you try to calculate the daily expenditure, and you've only taken randomly one day for one of the states, versus you took maybe the entire year to calculate daily expenditure for the rest of the states. Now, obviously, you have more information if you had information about the entire year and you computed an average, right? You just divided by the number of days you had than if you only had one day. So that's why you need to account for the variable exposure also by weighting the observations. But fortunately, there's another way of doing that is simpler, and that most software will allow you to do. So with a little bit of manipulation of logarithms, and you don't need to necessarily remember that, but it can be easily seen that if you take the same formula, so it's the same formula as before, but if you use the properties of logarithm, and one of them is that if you take a fraction here, lambda over exposure, if you take the logarithm of that, it is actually equal to the logarithm of the numerator minus the logarithm of the denominator. It's a very practical convenience of logarithms. So you could compute the second line here from this property of logarithms. And then if you just change a little bit the expression, that allows you to keep on the left side of the equation, still the logarithm of lambda like we had before. And what's new here, however, compared with before, is that you have a new term, which is the logarithm of the exposure, which we see here on the right. Now, the thing is, you don't see a slope in this model, and we're not really used to that. We're used to having each of our terms, right? Each of our predictors and the intercept have a parameter, right? Beta 0 plus beta 1 income. And here we just have the logarithm of the exposure. There's no, actually there's no beta. So ln of exposure, the logarithm of exposure, is now treated as a predictor, very similar to a predictor. That's going to be very practical. In a way, it's a little bit like a predictor whose slope is fixed to 1, right? So it's a little bit like it has a slope, but this slope is 1. And so whenever we have a situation like that, we say that this, like this, the logarithm of exposure, it is called an offset. Okay, so we have an offset that is here the logarithm of exposure. So it's important to note here that if you want to use as offset the logarithm of exposure, you're going to have oftentimes to compute it. In this example in SPSS, I took the exposure and I just used the ln function on it to compute the logarithm of the exposure. And then when you're in the generalized linear model menu, you can actually provide the offset variable directly when you specify your predictors. Okay, and so once you have that, you can then fit your model. And what's interesting, by the way, about doing that is that when you use this way of so again, you could weigh your observations and you could predict daily expenditure instead of monthly expenditure in this example. That allows you to account for exposure in the same way. The only problem with that, is that one of the problems of that is that you get a prediction of daily expenditure, right? So if you were interested in monthly expenditure, that means you still have to do additional computations to recompute predictions for months after you fitted the model, because after all, you don't predict lambda, you predict lambda over the exposure. So here, that's the daily expenditure. Here, if you still want to predict monthly expenditure, you just need to add a term of prediction, which is the offset term, and that's it. Your prediction is still then a prediction of monthly expenditure. Okay, and so you see, you also you get really similar output to what an output that is really similar to what you usually get. And likewise, you can get tests of your model effects that include this log exposure here as offset. But you need to keep in mind this log aspect, which is, of course, very, very important. Okay, so we've covered the most important topics when it comes to Poisson regression. Thank you for watching.